Okay, hello everyone. Welcome to week 7 of the live interactive sessions for the course Integrated Waste Management for a Smart City, offered through NPTEL. And I am Sedu Vinayagan, a PhD scholar in the Civil Engineering Department at IIT Madras. Yeah, let's start with the overview of the lectures covered in week 7. So the first lecture of week 7 covered about composting. So the first three lectures were about the biological treatment, and the last two lectures were about thermal treatment. So in the biological treatment, we looked at one technique, which is composting, which is an aerobic degradation of the organic waste. So we looked at so this was a continuation. So we looked at different factors that affect the composting process at the end of previous week. So in this week we continued with We looked at the air requirement and water requirement, and also then a need to destroy the pathogen so that this compost can be used as manure for agricultural purposes. And then in the second lecture, lecture 32, we looked at the different techniques that are out there for performing composting, and also looked at some example problems on how to do this compost design. And then we moved to the anaerobic digestion. So some basics about this anaerobic digestion, which is degradation of the organic matter in the absence of oxygen. And then in the third lecture, we looked at some more examples of composting, how to find out the air requirement or the pump requirement, right? So because we need oxygen, and we cannot directly supply, we won't directly supply oxygen in that, so therefore we supply air to meet the oxygen requirements, and which indirectly translates into the requirements of the pump, right? So the pump has to be used for supplying the air. So based on how much air has to be supplied, we look at how what should be the requirement of the pump that should be used. And then in the fourth lecture, we moved into the thermal treatment, right? So it is another way of managing it. So we try to in the thermal treatment, we try to use heat, we try to burn the waste, right? So that is one of the solutions that can be adopted. So in the thermal treatment, how it forms a part of our integrated waste management plan, right? And then in the final lecture, we looked at some basics. So the fourth lecture was an introduction to the thermal treatment, and then in the last lecture, we looked at some of the basics of this thermal conversion process. Right, so with that, we'll start this week's problem solving session. So the first question is about the anaerobic digestion. So there is a sequence of steps that take place in the anaerobic digestion. So a different combination of these steps are provided here, and we have to pick the correct sequence of these steps that take place in the anaerobic digestion of the organic waste. So there are four options. So the four broad steps that take place are in no particular order, or hydrolysis, acidogenesis, methanogenesis, and acetogenesis. So we need to find out which is the right order, right? So the right order is actually option B. So we start with the hydrolyzing. So the hydrolyzing bacteria, that is what will first act on the organic waste, and followed by the acidogenesis, where the acidogenic bacteria will try to produce some high molecular weight acids. So then the third step is the acetogenesis, where the acetogenic bacteria will produce the acetic acid, which is a low molecular weight acid. And finally, this the end product of that will be used by the methanogenesis, the methanogenic bacteria, to provide the end product of methane, right? So this is the sequence of steps that takes place in an anaerobic digestion, and therefore the correct order is as given in option B. Okay, is if there is any question, so please feel free to stop me in the middle and ask. Okay, so then moving on to question number 2. Which of the following is the food for methanogenic bacteria in the anaerobic process? Options are hydroxyl groups, methane, acetic acid, proteins, and lipids. Right, so this is an extension of the previous question, right? So this here we are focusing on one particular step within that anaerobic digestion, which is the methanogenesis, right? So the production of methane. So the methanogenic bacteria acts on this. So it takes something, so it needs a food source, and then it converts that into the methane gas, right? So here the question is, what is the food source? So the answer to this is option C, acetic acid. So why is that? To answer this, we can look at again where this step takes place. So if we look again, recall the previous question. So the methanogenesis is the last step of this anaerobic digestion, right? So for that, before this methanogenesis takes place, the acetogenic bacteria acts on the organic waste and then produces the acetic acid. So the output of, or the end product of the acetogenic bacteria, which is the acetic acid, becomes the food for the methanogenic bacteria. Therefore, option C is the right answer. So the acetic acid is what is taken by this methanogenic bacteria and then converted into methane. Okay, any questions? All right. Moving on to question number 3. So here we have to match the items given in column A to those in column B. So we have different composting techniques listed out in column A. We have windrow composting, aerated static pile composting, and in-vessel composting. And in column B, we are given three different ranges or durations, which is the composting time. So we have to match the composting technique with the time it takes for completing the composting using that technique, right? So we have different options given here, listing different matches. So maybe we can do this as a poll. So you can take a couple of minutes to recall and think about which composting technique takes what amount of time, and then answer it in the poll. So I'll create a poll in the meantime. Okay, the poll is live now. Yeah. So we have two answers. So both are option C, and that is the correct answer. So where we have windrow composting, usually takes 1 to 3 weeks, and aerated static pile composting 3 to 5 weeks, and the in-vessel composting taking 4 to 7 days. Right. So windrow composting is where we have these windrows or these piles of organic material that are called windrows, and then these material will be regularly mixed, right? So the whole organic matter will be regularly mixed, and while mixing, air is mixed with this organic material. So in this process it takes about 1 to 3 weeks. Whereas if you go for a static pile, as the name suggests, the static means the matter, organic matter, is not disturbed, right? But we will have air blown through this compost, right? Because air is needed, we need to supply air because we are not turning or mixing this organic matter. We blow the air through this static piles. So either we blow into the compost, or we will create a negative pressure vacuum so that air is sucked into it, right? So either there will, and then this process is comparatively slower, and therefore it takes about 3 to 5 weeks for this process to complete. And the final one, the mechanical or the in-vessel system, is what is followed in the industrial systems, and it is a closed system, closed reactor, right? So here, this is the fastest way of doing the composting, where it takes only 4 to 7 days, right? So the compost keeps on moving in these different layers, and then air is continuously supplied, and therefore this process completes rapidly in about 4 to 7 days, right? So that is the correct match of the composting technique to the composting time, which is given in option C. Okay, so moving on to question number 4. This is a numerical question. So we need to calculate the oxygen requirement for the complete combustion of 100 grams of ethane. So the options are 3.73 grams of oxygen, 37.3 grams, 373.3, and 3733.3 grams of oxygen. So again, you can take a couple of minutes to solve this and answer in the poll. Okay, we have one answer. It's 373.3 grams. Let's just wait for 1 more minute for others to complete. Okay, there is no other answer. So yeah, so the correct answer is actually option C, 373.3 grams. So now we'll look at the step-by-step solution. Okay, so the question asks about the oxygen requirement for the complete combustion of 100 grams of ethane, right? So first we should write the chemical equation for the combustion of ethane. So the chemical formula for ethane is C2H6, right? So that is ethane. So we are talking about combustions, which is an oxidation process. So we need to supply oxygen, right? So once oxygen is supplied, so upon complete combustion, when there is complete combustion, the end products are nothing but carbon dioxide and water, right? So this is these are the end products or the output when ethane completely undergoes combustion. So but this is not balanced, so we should balance this equation so that the atoms or the masses are balanced. So when you balance it, you get 2 moles of ethane reacting with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water, right? So this is the balanced chemical equation for the complete combustion of ethane, right? But now we are talking about only 100 grams of ethane. So what is the molar mass of ethane? So molar mass of ethane is nothing but so carbon, we have 2 carbon atoms, so that is 24 grams, and there are 6 hydrogen atoms, so that is 6 grams, so totally 30 grams per mole, right? So that is the molar mass of ethane. And similarly we can find the molar mass for oxygen gas, which is O2. So for that we'll get 7 times, 16 grams per mole, right? So that is the molar mass for oxygen. Now since here we know 2 moles of ethane requires 7 moles of O2, right? So which means 60 grams of ethane, right, requires 7 moles sorry, this is actually 32 for, because oxygen there are 2 atoms, it will be 32 grams per mole for O2 gas, right? So it requires 7 moles. So for 1 mole it is 32 grams. So for 7 moles it will be 224 grams, right? So we know 60 grams of ethane will require 224 grams of O2. Right? So from the balanced equation, we know this information. The question is about 100 grams. So from here, we can calculate what will be the oxygen requirement for 100 grams. So O2 required for 100 grams. So how do we do that? So for so 224 is needed for 60 grams. So for 100, it will be 224 into 100 by 60. So that is 373.3 grams. Okay, is that clear? So for every 1 gram, we'll require 224 by 60 grams, right? For 100 grams, it will be 224 by 60 times 100. Any questions? Okay. Okay, now okay, let's continue with question number 5. What is the temperature range of the mesophilic bacteria? So the options are 293 to 303 Kelvin, 270 to 300 Kelvin, 303 to 311 Kelvin, and 328 to 333 Kelvin. Right. So we saw about two types of bacteria, right? When we talked about in the lectures when we looked at the biological treatment, mesophilic and the thermophilic. So these operate at different temperature ranges. So for the mesophilic bacteria, the optimal temperature range is 30 to 38 degrees centigrade, right? So that was given in the lecture, right? So for mesophilic, it operates in 30 to 38 degrees centigrade, and the options given here are in Kelvin. So to convert from Celsius to Kelvin, you need to add 273, right, approximately. So 30 translates to 303. So 30 plus 273 is 303 Kelvin, and 38 plus 273 is 311 Kelvins. Therefore, the temperature range for the mesophilic bacteria is option C, which is 303 to 311 Kelvin, right? So just you need to be careful with the units, right? So because here we have converting from Celsius to Kelvin, so you need to pick the appropriate answer based on that. Moving on to question number 6. What is the ideal pH range for the anaerobic digestion of waste? So the options are 6 to 7, 7.5 to 9.5, 6.5 to 7.5, and 7.5 to 8.5. Okay, so again, because there are different types of bacteria working on the organic matter, so the pH range becomes important because it is different for the different types of bacteria, right? So for example, the acidogenic or the acetogenic bacteria, they produce acids which lowers the pH of the system, whereas for the methanogenic bacteria, we'll need a higher pH for it to work effectively. Therefore, we need a balance between these two, and therefore there is an ideal range which is better for this whole anaerobic digestion process. So that range is actually 6.5 to 7.5, which is option C. Right. So we saw this. So the ideal condition is 6.5 to 7.5. So when it drops below 6.2, it is not favorable for the methanogenic bacteria. Therefore, we should make sure that it's between the 6.5 to 7.5, right? Because of these different types of bacteria, therefore the pH needs to be ideal so that everything works perfectly. Moving on to question number 7. Here we need to calculate the biological volatile solids, or the BVS fraction or the BVS content for the given waste composition of an agricultural waste. So the composition is, there is a moisture content of 26%, and the volatile solids are 80%, and then there is a lignin content of 5%. And the options are 0.69, 0.66, 0.78, and zero point 0.8. Right, again, you can take a minute or two to solve it and answer in the poll. So we need to use the given information on the composition to find out what will be the content of BVS. Okay, we already have an answer in the chat. Just wait for some more time for others to catch up. Okay, do we have any other answers apart from option A? Okay, so the correct answer is option A, 0.69 or 69%. Now we look at the solution. So how do we calculate the BVS? So we have an empirical equation that relates the biological volatile solids to the lignin content, right? So that empirical equation is BVS content is equal to 0.83 minus 0.028 times the lignin content. And in this equation, the lignin content is expressed in percentage, right? So if it is 5%, we should replace LC with 5, right? So this is an empirical equation derived from past studies. So we use this. So we don't need the information on the moisture content and the volatile solids, right? So we just need the lignin content. So that is 0.83 minus 0.028 into 5, right? So if you solve this, you'll get BVS equal to 0.69 or 69 percentage, right? So that is option A, and therefore that's how you solve for the BVS given the lignin content, or you can use this to find the other way around. So if you are given the BVS, you can use that to find the lignin content as well. Okay, any questions? All right, so we'll move on. So question number 8 is the thermal processing of waste in the absence of oxygen is called dash. So the options are incineration, plasma arc, pyrolysis, and gasification. So we looked at different ways of processing, thermally processing waste in the lectures, right? So we looked at so all these options are what were covered in lectures, but here we are talking about that process where oxygen is not used, right? It takes place in the absence of oxygen. So the one that takes place in the absence of oxygen is option C, pyrolysis, right? So we looked at combustion, pyrolysis, gasification, and plasma arc. So combustion is what takes place in the presence of oxygen, right? Oxygen is needed, and there are again different types of it. And pyrolysis is where oxygen is not used. And then we looked at other processes that are less frequently used, such as gasification and plasma. Okay, moving on to question number 9. The organic fraction of the biodegradable component that gets destroyed, here by destroyed we mean which reacts during the biological treatment, is termed as dash. The options are the inorganic solids, fixed carbon, biological volatile solids, and residual volatile solids. So maybe we can do this as a poll. Okay, we already have an answer in the chat. Yeah, C. Any other answers? Yeah, other answers also C. Yeah, so the right answer is C. So if you remember the pie chart which shows the composition of waste, so we have these different components, which is BVS or the biological volatile solid. We have some moisture or water and some inorganic components, and then the residual volatile solids, right? So out of these, the one that biologically reacts is the biological volatile solid, right? So it is the organic fraction that reacts during a biological treatment. The other parts, such as the RBS or the residual volatile solid, so as the name suggests, it's a residue, right? It won't react; it comes out of the treatment process unreacted, right? So that is the even though it is an organic fraction, it will not be acted upon by the by the microorganisms. And inorganic, so because it's inorganic, it will not be acted upon, and moisture will also is required, but it will not react, right? So it is only this BVS fraction that is going to be treated in the biological treatment, right? So that is given in option C. Moving on to question number 10, what are the advantages of the thermal processing of waste? So the options are loss of energy, energy recovery, volume reduction, and both energy recovery as well as volume reduction, right? So thermal processing, again, there are different techniques to do it, and different techniques will offer different advantages. So here we are talking about in general about the advantages of thermal processing. So generally we do that for two reasons, which are option which is given in option D, both B and C. So for both doing energy recovery as well as volume reduction, so these two are both potential uh, we can say benefits that we can derive from the thermal processing, right? So mainly we will get volume reduction. So the volume will be reduced when we do the thermal processing, either combustion or pyrolysis or whatever it is. So volume will be reduced, right? So that means we will have less volume of waste that needs to be disposed into the landfill, right? So that saves us space and extends the life of the landfill, right? So that is the major advantage from doing the thermal processing. So that is for volume reduction. And if we are smart about it, we can also recover some useful energy in this thermal processing, right? So we could when we use high calorific waste, so we can derive energy out of it, and this energy can be used for other processes such as generation of electricity or heating of homes or whatever it is. So we could do that as well. So both energy recovery as well as volume reduction are advantages that we get out of the thermal processing of wastes. Okay. Moving on to question number 11, which of the following statements are true regarding the anaerobic digestion? So the options are batch systems produce low methane than the two-stage system. Batch systems are ideal for developed countries. A two-stage system of anaerobic digestion is better than the batch system, and batch systems are producing more methane than the two-stage system. So the questions from now on are multiple select questions, so more than one option could be correct. So, what do you think are the statements which are true about the anaerobic digestion process? So, we looked at these two types of systems, right? One is the batch system, other is the two-stage system. Okay, we have one answer saying B and D. Okay, D. Okay, any other answer? We have B and D. D. Okay, so the right answer is actually A and C. Neither B nor D are correct. So, but A and C both are correct. So the batch system we get lower methane than in the two-stage system, and so that makes option D false, right? So, and option C is a two-stage system is better than the batch system. Why? Because in a two-stage system we have separate the acidogenic and the methanogenic phases are separated. We saw that these two phases are different, right? So they require different conditions. So by separating them, it becomes the process becomes much easier and better to handle, right? So in that way, a two-stage system will be much better for the anaerobic digestion. So if you recall from the lecture, so we discussed about these two. So the batch systems is better for the developing countries, but there will be low methane production from it. So it doesn't require very high tech systems. Whereas two stage, it requires more cost because we need separate stages for the acidogens and the methanogens. Because of that, there will be more cost. Therefore, it is not developing countries may not be able to adopt such systems on a large scale, but it provides it works much better than the batch system, right? So that's the trade-off that we are making between going for a batch system and the two-stage system. Okay, moving on to question number 12. What are the different inorganic compounds that are present in a solid waste? So the options are metals, cellulose, proteins and fats, glass. So which of these are the inorganic compounds that we find in a solid waste? Yeah, we have an answer A and D. What about others? Do you agree with that? Okay, all. We have one answer saying all. Okay, do we have any other answer? Okay, so the right answer is actually only A and D, metals and glass. See, the question is only asking about the inorganic compounds which are in the solid waste, right? So out of the given options, inorganics are the metals and glass, right? So it is the metal, glass, and there will be other inorganic components as well. But out of the options given here, it is only the metal and glass which are the inorganics that we find in the solid waste, right? So cellulose, proteins, and fats. So those are the organic components. So it's only the metals and glass which are the inorganic compounds. Okay, is that clear? Okay, so moving on to question number 30. What are the different combustion aerobic techniques of thermal processing of solid waste? So the options are pyrolysis, incineration, plasma arc, and cogeneration. So just a few questions back, we looked at the different techniques. So here the question is, which of these are the aerobic techniques of thermal processing of the solid waste? Okay, B and D. B. other answers? Okay, so the right answer is actually B and D. Both incineration as well as cogeneration are aerobic techniques, right? So we looked at four different ways, four different processes of that comes under combustion itself. So incineration, cogeneration, energy from waste, and co-incineration. So these are different names or terminologies that we use. So both incineration as well as cogeneration are used as aerobic techniques. We already saw pyrolysis, how it is takes place in the absence of oxygen, and plasma is again, it doesn't come under the combustion. It's about taking it to an ionized state, right? So whereas in combustion we just use oxygen to burn it to
Sir,
completely.
what is co-generation?
Okay, cogeneration. So in when we say incineration, it is we are only focusing on burning the waste to reduce the volume, right? So in the incineration, our intention is not really to generate or to derive energy from it. Whereas when we are talking about cogeneration, it is both burning the waste as well as when we are generating electricity out of it, or energy, deriving energy out of it, right? So that is what we mean by cogeneration. But in both process we use oxygen to do the combustion. Okay. Any other questions? Okay, so there are no other question. Question number 14 is, which of the following statements are true about the composting technique? So the options are, the carbon to nitrogen ratio of the compost should be greater than 25 is to 1. The compost material is agitated periodically in agitated composting. The compost contains a more diverse microbial population. And D, the carbon to nitrogen ratio of the compost should be less than 25 is to 1. Okay, we have one answer, option A. Any other answers? Okay, C and D. Okay, another option, another answer, C and D. Okay. So the right answers are actually all the three, B, C, and D. Right. So B, C, and D are all correct statements. So the compost material. So when we say agitated composting, so as the name suggests, the compost material is agitated in this particular technique of agitated composting. And when we cure the composting, once that required composting time is given, after that we cure the compost for some more time where the temperature is brought down. So in that period the compost will also develop a more diverse set of microbes in it, right? So that is also a true statement. And in option D, again during that curing period, the carbon to nitrogen ratio will come down to less than 25 is to 1. So there will be more nitrogen being added, right? Or the carbon will be reduced, so that the final ratio will be much less than less than 25 is to 1. So that is more advantageous for when we use it as a manure, right? So we need more nitrogen as a nutrient for the plant growth. So that is also achieved at the end of this composting process. So both all the three, B, C, and D are true statements, right? So we don't need a high carbon to nitrogen ratio. So option A will become false, right? So we looked at this. So during when we looked at the composting process, right? So once the compost is done, right, through whatever process, it is cured for a further period of time, and during this period all these conditions occurs, right? So it is stored in a dry condition, and some occasional mixing will take place, and it is in that time there will be a diverse microbial population, and also more nitrogen will be occurring, and therefore the ratio of carbon to nitrogen will be less than 25:1. And during this period the temperature will also come down. Why is that required? Because this will be used in the farmland, where when we use the seeds the temperature should not be so high that the seeds cannot survive, right? So those things will happen during this curing period. And with respect to that agitated technique, so either we have two broad ways. So one is the agitated, or where we mix it, and the other one is the static one, where we do not mix the organic material. Instead we the blow the air through the compost material, right? So those are the two broad ways. So when we say agitated, so the mixture or the material will be mixed or agitated periodically. So by while doing that, the air will be introduced into it. Okay, so that's why all the three options were correct. Any questions? Okay, so yeah, so that concludes the questions that we have for week 7. So if you have any other clarifications or questions from the lectures, you can ask. Otherwise, we'll conclude the session here. I'll wait for a few more minutes if you have any questions, and then we can wrap up the session. Yeah, thank you. If you have no further questions, you can feel free to um, end with the call. Yeah, yeah. The recordings will be made available. So all the previous weeks are already available on YouTube. So in the course page on Swayam portal, you will find the link to the YouTube channel. So the PDF, the PPTs that are being used are also being shared. So the PDF version of it, along with the recording of these sessions, are made available. So you'll find the links in the course page on the Swayam portal. Okay, so there are no questions. We'll conclude the session here. Thank you all for attending. We'll meet again next week.